This meeting is being recorded.
In this last section of chapter 14, we're going to look at what's referred to as the degrees of unsaturation. So this term indicated up here, and this is sometimes referred to as the HDI or hydrogen deficiency index. So the HDI. So mass spectrometry, we know, can be used to determine a molecular formula, as IR can be used to determine the functional groups present in a compound. But an extra type of determination, such as using the hydrogen deficiency index or finding the degrees of unsaturation, can help us more specifically refine what compound we may be looking at. So neither of these fully elaborate the structure of the compound. Just the molecular mass, aka molecular formula, can be deduced, but the arrangement of bonding sometimes is not apparent. So we know that alkanes are called saturated hydrocarbons because as many hydrogens as possible saturate the bonds, right? So we have this formula given here where carbon has a subscript of N, so that could be N equals 1, any positive integer, and we would plug in that same integer for hydrogen here. So we have this formula C to the N, and then H to the 2N plus 2 that indicates that we have an alkane or a saturated hydrocarbon. But at times, we have alkenes, we have alkynes with double or triple bonds. We also have rings or cyclic structures. These contribute to what we refer to as a degree of unsaturation. So a pi bond or a ring, both of these would, again, add a degree of unsaturation, whereas we have to remove hydrogens to form bonds or to form rings. And every degree of unsaturation, we have the number of hydrogens specifically reduced by 2. So we have in our double bond shown here, so we go from pentane to pentene, and we have 2 less hydrogens, and then we can go to pentyne with a triple bond, and then we have 4 less than our saturated hydrocarbon. So both of these over here, these are considered unsaturated, and they have 1 degree of unsaturation. So we could say the hydrogen deficiency index equals 1 here, or we have an index of 2 here. So 2 degrees of unsaturation, right? 4 hydrogens have been removed from the saturated comparable alkane. So again, when we have unsaturation, we know that that means we remove hydrogens, but we can have some different isomers possible with the same number of carbons and unsaturated amount of hydrogens. So here we can see that C4H6 can be represented in many different ways. We know that there are 2 total degrees of unsaturation. So we can have that with either 2 double bonds in either conjugated or accumulated, like shown here. Then we have 1 triple bond, each of which has 2 degrees of unsaturation each. So that's another way to represent this. We could have 2 rings, 2 degrees total, or we could have a ring and a pi bond. So any of these combinations would produce the same amount for our hydrogen deficiency index, or 2 degrees of unsaturation. So how can we figure this out? Well, we can look at, in general, when we have hydrogens present on our molecule, we can compare to how changing that hydrogen to something else will affect our count. So say we have chloroethane, for example, we would treat a halogen as if it were a hydrogen because it doesn't affect our degree of saturation. So the same happens with oxygen. We know that oxygen does not affect our numbers of hydrogens overall. So we would, in turn, when we look at our formula, we're going to subtract 1 for halogen, so minus for every X, whereas for oxygens, there's no indication of this in our formula that we're going to use. So let's take a look at what that means here. So say we have a compound, so our ethylamine here versus ethane. And we saw that when we added a halogen or an oxygen, the halogen would remove a hydrogen, the oxygen would not affect the number. Nitrogen actually adds one hydrogen for every nitrogen. So we have this formula shown down below to calculate our hydrogen deficiency index. And this would determine our degrees of unsaturation for us. So say we wanted to plug in values for ethylamine here, we could see that we have 2 carbons, so we would plug in 2 times 2 plus 2 plus 1 nitrogen, and then we would subtract 1, 2, 3, 4, 5, 6, 7 hydrogens. There's no halogens, so let's see. We have 4 plus 2 is 6 plus 1 is 7 minus 7 equals 0. So what this tells us is that ethylamine has a 0 degree of unsaturation. So as we can see, there's no cyclic structure involved, there's no double bonds, no triple bonds. So this makes sense that we have a 0 for our degrees of unsaturation. Say we did the same thing, but instead of using ethylamine here, say we compared our numbers for ethene. So ethene, let's draw that out. We know that it would be, instead of C2H6, we would have C2H4. So let's plug in some numbers here. So we would have 2 times 2 plus 2, there's no nitrogens, and then subtract 4, there's no halogens. So we have 4 plus 2 gives us 6 minus 4 gives us 2, and then we would have 2 times 1/2 is the same as 2 divided by 2. So we end up with 1 degree of unsaturation, and if we know the structure of ethene like we do, we could draw it and confirm that there is 1 degree of unsaturation. So this can be a very useful concept, this calculation of degree of unsaturation, when you're comparing structures, whether or not you have similar infrared spectra. If your structure does not have any rings or double bonds or triple bonds present, you're going to see that HDI of 0. And then for every ring, double bond, you'll have 1 additional degree of unsaturation, and then with a triple bond, you'll have 2. And again, this can be very useful when you're comparing similar spectra.